Hello everyone, I'm Tiantan. I'm going to present our paper, Making Pointer Analysis More Precise by Unleashing the Power of Selective Context Sensitivity. This is a joint work with Yueli, Xiaoxin Ma, Chang Xu, and Yanis Markadakis. In this work, we propose a new pointer analysis technique for all programs. Pointer analysis is a fundamental static analysis that determines which objects a variable can point to during runtime. As a fundamental analysis, pointer analysis is used by many clients and implemented in many analysis tools. So precise pointer analysis can benefit all these clients and tools. It has been demonstrated that context sensitivity, CS for short, is one of the most successful pointer analysis techniques for producing high precision for all programs, and it has been widely adopted by many static analysis frameworks for all programs. The idea of context sensitivity is to distinguish points to information of the methods by their different calling context. Although CS can significantly improve precision, it suffers from a well-known problem, scalability issue. In a context-sensitive analysis, each method is analyzed under one or more contexts. This may cause heavy efficiency cost, which makes it hard to scale for large and complex programs. Here I say an analysis can scale for a program. It means that analysis can finish for the program within reasonable time budget. To address the scalability problem, recently, there's a trend of selective context sensitivity. This technique is based on two key observations. First, only part of the methods in a program can benefit from CS. It means that applying CS to only these methods is useful for gaining precision. We call them precision-useful methods. Second, in hard-to-analyze programs, there exist some dangerous methods that applying CS to them will blow up the analysis in complexity and make the analysis unscalable. We call them scalability threat methods. The idea of selective CS, as shown in this pie chart, is to apply CS to only part of the program and context insensitivity, namely CI, to the other part. Ideally, we should apply CS to precision-useful methods and CI to scalability threat methods. Recently, there are quite a few work about selective CS pointer analysis get published at top conferences, and they can improve scalability while being significantly more precise than CI. Despite effective, selective CS has a limitation. These techniques need to make careful trade-offs between precision and efficiency. If we want to gain better precision, then selective CS usually has to sacrifice efficiency by applying CS to more methods, which may even threat the analysis scalability. Namely, one more step towards precision may put the analysis at the risk of unscalability. Such a position between precision and efficiency makes it hard to further improve precision by selective CS. However, empirical study shows that for many real-world applications where points to or alias information is required, such as certain bug detectors, security analyzers, and so on, good precision is much favored, even if the price is to run the analysis for a long time, such as several hours. So in this work, our goal is that, given alone a reasonable time allowance, we aim to achieve precise pointer analysis results for hard-to-analyze Java program for which traditional CS fail to scale and selective CS scales but with limited precision. Our key insight is that each selective CS approach has its own insights to select precision-useful methods and avoid scalability threat methods, but also limited by it. This is like in a murder case. Police officer, medical examiner, private detective, and journalist are seeking the truth. Each of them has own perspective, but also limited by it. But if they can collaborate, it will dramatically increase the chance to catch the murderer. Similarly, to unleash the power of selective CS, we propose to incorporate different selective CS approaches. Based on the insight, we propose unity relay. It is a meta framework to produce highly precise point analysis for hard-to-analyze Java programs by incorporating different selective CS approaches. It takes a program P and a set of selective CS approaches S as inputs, and outputs precise pointer analysis results for P. Unity relay is a one-two punch. It first provides a mechanism called unity, and when unity fails to scale, it offers a scheme called relay. Now I will introduce unity and relay respectively. Recall that every selective CS approach represents a precision and efficiency trade-off, and pursuing better precision may cause scalability issue. Now it seems that we are trapped. A small step towards precision may hit a scalability wall. In this situation, how to reap noticeable precision improvement in a general meta framework? Well, to escape from the trap, actually our solution is quite counterintuitive. We propose to take a big step forward towards higher precision and apply CS to many more methods with heavier context elements and longer context lengths, if possible. Based on this proposal, we design unity, and we will explain why such a proposal works well when we introduce unity. Now let's present the working mechanism of unity. Given a set of selective approaches, say S, unity applies CS to all methods selected by the approaches in S. For example, here, these squares represent all the methods in the same program, and S consists of 3 selective approaches, S1 to S3, and each approach selects part of the program to be analyzed with certain context sensitivity variants. For example, S2 selects 2 type sensitivity for these methods, and S3 selects 3 object sensitivity for these methods, 1 type sensitivity for these methods, and 2 object sensitivity for these methods. The gray part of these squares means that the selective approach selects CI for these methods. Then in unity, we apply CS to all the selected methods as shown in this figure. For the methods that are reported to be analyzed with CS by model 1 approach, unity finds out the most precise configuration. For example, for these methods, S1 select 2 obj for them, and S3 select 3 obj. Since 3 obj is more precise than 2 obj, as it has longer context length, unity applies 3 obj for these methods. Apparently, unity is more precise than any approach in S. Someone might think unity takes a big step forward towards higher precision and looks much more expensive. Is this still scalable? Actually, we expect that unity still has good scalability, and this is the reason. Note that each of the selected methods is determined as not a scalability threat by at least one approach in S, even if it is analyzed under the most precise configuration. And we found that avoiding scalability threat methods is the key to scalability, but the number of the methods analyzed with CS is not the key. As a result, although now possibly many more methods are analyzed under CS with more precise configuration, we still have a chance to obtain a scalable analysis. Consequently, unity exhibits good scalability in our evaluation. However, we cannot ensure that unity is always scalable. After all, it is indeed more expensive. So we propose relay, which comes into play when unity fails to scale. The idea of relay is to divide the scalability burden of unity into different passes. Here, each pass is a round of selective CS pointer analysis. In relay, the precision achieved by formal pass can be transmitted and accumulated in the next pass through a technique we propose, called precision filtering. Now I will introduce the 2 options of relay, O1 and O2. Given a set of selective approaches, relay O1 runs n passes. Each pass corresponds to a selective approach in S. The upper figure illustrates relay O1, and let's explain it by comparing to unity. Similar to unity, relay O1 combines different approaches to generate the most precise configuration for each method. But we can see, for pass I, relay O1 only applies CS to the methods reported by SI. Such a strategy still keeps the most precise CS configuration, but applies CS to less methods. Thus, it's more likely to scale compared to unity. To gain precision as much as possible, we design a filtering mechanism in relay, represented by these funnels. Filtering mechanism uses the positive results of formal paths to filter out spurious objects in later passes. For example, suppose that path 1 reports that V points to O1 and O2. And in path 2, the pointer analysis concludes that V points to O2 and O3. But by path 1, we know that V cannot point to O3. Thus, we can filter out O3 from the positive side of V during path 2. This is like a relay race, which delivers the precision of each path like a baton. That's why we call this technique relay. With filtering, we can ensure that each path in relay is no less precise than previous passes, and the precision of different approach can be accumulated over passes. Although uncommon, what if relay O1 is not scalable? To ensure scalability, we design relay O2 as the last line of defense of unity relay, as illustrated by the upper figure. Relay O2 employs the same principle as relay O1, except that for path I, relay O2 does not use the most precise configuration. Instead, it uses the same CS configuration as reported by input selective approach SI, and these figures shows the difference between relay O1 and O2. So above is the introduction to our unity relay framework. In our paper, we have proven two important properties of unity relay: precision and scalability guarantees. If you have interest, please read the paper for details. Here I just present the conclusions. Given a set of selective approaches S, with unity relay O1 and O2, we can guarantee that the precision of unity relay is better than or at least equal to any SI in S. Besides, with relay O2, we can guarantee that if S1 to Sn can scale for program P, then relay O2 can also scale for P. In a word, given a set of scalable selective approaches S, unity relay can always produce a point analysis that is practically more precise than any SI in S, and is also scalable. As a proof of concept, we introduce Baton, an instantiation of unity relay framework. For better precision, the chosen approaches of an instantiation should be diverse, so that they could cover precision useful methods from different perspectives, and they should exhibit good scalability. Accordingly, Baton considers three such approaches as inputs: collection, based on expert experience; zipper E, based on precision loss pattern; and scalar, based on bounding our points to size. Now let's see if unity relay can achieve our goal. We run Baton for how to analyze Java programs to evaluate its precision and scalability. Specifically, we compare Baton against two state-of-the-art selective CS approaches, zipper E and scalar, to evaluate how much more precision Baton can achieve. In our evaluation, we analyzed 13 hard-to-analyze Java programs, including some decoupled benchmarks and real-world apps. We measure the precision via 7 precision metrics, including 3 general metrics and 4 widely used clients. These include all hard-to-analyze programs and all precision metrics in recent literature for Java pointer analysis. In summary, Baton can scale for all 30 programs, which validates the scalability guarantee, and it achieves the best precision for all precision metrics in all programs, which validates the precision guarantee, and the difference in precision is often significant. For example, Baton improved the precision of alias pairs, one of the 7 precision metrics, for programs Heritrix, Galleon, and Jasper reports by more than 50% and up to 71%, compared to the previously best algorithm. It is the first time that these levels of precision are obtained for these hard-to-analyze programs. In this work, we propose unity relay, a general meta framework for producing highly precise point analysis for hard-to-analyze Java programs. Unity relay systematically exploits selective CS approaches with precision and scalability guarantees. We designed Baton, an instantiation of unity relay framework. In our evaluation, we can achieve currently the most precise results for hard-to-analyze Java programs, and its precision is well beyond existing approaches. Baton is merely one instantiation of unity relay framework. We expect more instantiations to unleash the power of more effective selective context sensitivity approaches, including the ones that are developed in the future. Thank you for listening.